All right, this unit is starting our study on dilations. It is a kind of transformation that we have had a little bit of experience with, but not much at this point. We've mostly worked with rigid motions, which are transformations that keep the size and shape the same. Reflections, rotations, translations, all of those things maintain the size and shape. Those are isometries, keeping the measures the same. But a dilation is a little bit different in that it will enlarge or shrink an object by some scale factor, and overall the shape will stay the same. It's a proportional increase or decrease. So we'll see a few examples of that in this introductory lesson, and that's what this unit is going to be mostly about. So in exercise 1, what we can see here is it's been measured in inches. We could use any unit of measure and have, you could use centimeters, whatever you want. But for letter A, when a ruler is laid down, we have 1.5 inches for the large domino and 3/4 of an inch for the small one. If we're trying to determine a scale factor, what we always want to do is divide the new one by the old one. By doing that, what we essentially establish is what we would need to multiply the original by to get the new. So if you always go to the final product and divide that by the original, that is going to give you the correct scale factor. Another way you can check it is once you're done dividing, if your value comes out bigger than 1, then that means that you have an increase. So if you look at the old to new and it got bigger, then you should have a scale factor that is bigger than 1. If you have a shrinking sort of situation, like in part B here, then because it's going from new to old and getting smaller, our scale factor should come out less than 1. And that's what happens when we divide 1 by 1.5. We get a value that's a fraction between 0 and 1, which indicates that it did shrink. So we always want to divide the result by the original in order to get the correct scale factor. All right, and so as you see here, another way to think about a dilation is when we have electronic devices. When we try to enlarge or shrink things, we do so proportionally. You grab the corner of an object or you pinch to zoom, and all of those types of enlargements and shrinking are proportionally speaking, and so those are dilations as well. We have a center of dilation, we have a scale factor. Those are the components of dilation. So to get technical about it, the geometry of it, the dilation is going to be a function. We usually call it function d for dilation. It'll have a center point that we dilate from, and it will have a scale factor, usually denoted with the letter k. K will be positive, and it's a function that has an input and an output, just like our other functions do. So we have an original point, and then we have its corresponding prime. So a would become a prime, c would become c prime, and so on. So if A is the center of the dilation, so in other words, if the point that we're dilating is also the center, then it's just not going to move. That's what number 1 is saying, that the original point will stay the same. But most of the time, a point that we dilate is not on the center, and so it will move. So number 2 is 99% of the time what happens is that a point becomes its prime, and we end up making a ray that connects the center point to the original, and we have an enlargement or a reduction. So let's look at some examples of that. So in exercise 2, if C is the center point, so if we're dilating from point C down here, and we try to use our ruler to find the image of A after a dilation by a factor of k equals 2, what that means is if we take the distance from C to A, what we need to do is go back to C and travel twice as far as we would have from C to the original point A. That's how we'll find our prime. So if the scale factor is 2 and we originally had 2 inches, now we're going to need to go 4 inches, but we're going from that original point, from that center point, not from A. So C to A is one distance, C to A prime is the other distance, and those two distances need to be a scale factor of 2 with each other. So as you can see in the length equation here, the distance from C to A prime is double the distance from C to A. And that is because the scale factor was bigger, and so the scale factor got applied to the original segment. The original segment CA is what we multiplied by 2. If the scale factor is 1/2, well, we still think about what it was originally from C to A. That was 2 inches. So 1/2 of that is going to be 1 inch, and so CA double prime is 1/2 of CA. So we just apply the scale factor, whatever it is, to the original figure to get the new one. All right, on the next page, we're given triangle ABC. That's in here. And all my markings are already done here, so you can try to follow along step by step. Using a straight edge and a compass, find the images of B and C and label them with primes. So the first thing I did with this is I made a ray that extended segment AC. And you can just lay a ruler down or a protractor or whatever kind of straight edge you want to use and connect it through C and extend it farther than you think you might need. We're eventually going to try to double it because it says scale factor 2. So just extend it up to the top of your paper and do the same thing with AB. Extend it out past point B, not all the way across the paper necessarily, but farther than you think you might need. And in order to use the compass then, what we want to do is put your metal point right here on A, put your pencil point on C, and that establishes a radius, that establishes a distance. If you then pick up the compass and physically move it to point C and mark it again, what we've done is doubled the distance. We've kept that radius consistent, and so point C prime will have to be twice as far away as point C was. And we can do the same thing over here. Metal point on A, pencil point on B, and then pick up the compass, put your metal point on B, and mark over here where B prime would be. So why wouldn't A change? Well, A is the center of dilation. It says that we're using A as the center, so no need to move point A. If, remember that was the first part of the dilation definition on the previous page, is that if a point is on the center of dilation, it won't move. So only B and C are going to move here. All right, so for part C, explain why any points along either AC or AB will still lie on these lines after dilation. So AC, that infinite line here, and AB, this infinite line here. Why will any points along those still lie on those lines after dilation? So the reason is, as you can read for yourself here, a dilation is going to map a point so that its images lie on the ray, in this case with the original point A. So since AB and AC contain that center of dilation, when any point on them goes out or in, it'll simply move along that line. So we're maintaining that line whether we go out or in, it's all going to move along the same path. And dilations will always do that. We have an original path, we're going to move along that path either out or in toward the center. Now you can paraphrase that however you like, but that is the summary of why those lines will still fall on that same infinite line. And that's how I started it, right? I extended that line AB out because I knew that B prime was going to be somewhere on that extension. And the same thing with AC, point C prime had to be somewhere on that extension. Had I had a scale factor less than 1, I wouldn't have had to extend it at all because I would know that C prime is somewhere on the original line. And same thing with B prime. So we know it's always going to fall on the same line. So D is the midpoint of BC, and we're trying to find its image under the same dilation. So what we do is we do the same thing with our compass. Well, first we'd want to make a straight line that connects A to D and out farther. Set your compass to AD, pick it up, place the metal point on D and mark where D prime would be. All right, and we can also have segment B prime C prime drawn, so you can connect those with your straight edge as well. And then what we're looking for is, does it fall on B prime C prime? And it will. Point D prime, when you double with the compass, should fall right on B prime C prime. And to check using your ruler, if you were to measure the distance from B prime to C prime, it's 140 millimeters, 14 centimeters. You could do it with inches too, and you're going to find that it's exactly the same size on both sides. So it will fall on BC right at the midpoint. So how does the length of B prime C prime compare to the length of BC? What should happen is it should be double because the dilation scale factor was 2, and all sides of the original triangle should get doubled in the new one. You can measure it, and the measurements here show that it's 140 centimeters and 70, so it's done with a ruler, but just theoretically it should be, and it is. And then if we look at part F here, what else seems to be true about those segments? They're going to be parallel, and you can establish that by measuring the corresponding angles. You can check it by distances with a compass. There's various ways you can anecdotally check it here, but all dilations are going to produce parallel segments as well. So to summarize the properties of dilations here, if a dilation of a segment that isn't containing the center, so segment AB from point C, so neither of those points are on the center, what's going to happen is two things. First, the new segment is going to be either larger or smaller by the scale factor, whatever the scale factor is. So if it's greater than 1, it'll get bigger. If it's less than 1, it'll get smaller. And the second thing is the new image segment will be parallel to the original one. So both of those properties will happen every time we do a dilation. And lastly, the dilation notation here. The only thing in the subscript is the center point. We have to name the center point, and then we have an input and output.